Welcome back to ELE 210. I want to go back and solve one more circuit with Thevenin's theorem, very similar to a homework problem that you have. And this handout I've put in the week 3 reading session. Let's see. Yes, this is week 3, circuit theory 1, Thevenin's theorem under readings. So, it says Thevenin's theorem solution of resistive bridge circuit. So here's our circuit. You know, this is a classic Wheatstone bridge type of thing. We're going to use 2.5 volts so that we can use our A down 1000 or M1K, whatever you want to call it, to actually build this. But we have a circuit here which we cannot solve with our regular total resistance method because we have these we have two loops here, and we'd have to use some kind of simultaneous equations to we've actually got, if you want to count the total number of loops, you've got a loop here, you've got a loop out here, and you've got a loop here and a loop here. And for nodes, you've got 1 node, 2 nodes, 3 nodes, and 4 nodes. And probably could put a little better dot there. So we have this bridge circuit, but it turns out that this can be solved with Thevenin's theorem. Not every multi-loop circuit can be solved with Thevenin's theorem, but this one can. It's because it only has one source, that's going to help us quite a bit. But even then, we could, create circuits that would be hard to solve that way. But let's take a look at this one. Our classic steps: disconnect the load, deaden the independent sources, looking back from the disconnected load with independent sources deadened, compute the resistance that's seen. So if we get rid of the load, we have points X and Y. If we look from point X, we'll see a 2.2K resistor going to the plus side of the source, and we'll see again from node X, we'll see a 4.7K resistor going to ground. So point X looks at this thing and sees 2.2K going to the plus side of the supply and 4.7K going to the negative and ground side. And I'm just showing this shorted here because that's what's going to happen in our Thevenin analysis. In our Thevenin analysis, of course, we're going to wind up deadening this load by replacing it with a short. If I then go on and look at what I see from node Y, similarly, I'm going to see a 4.7K to the plus side and a 2.2K to the minus side and ground. And so I'm going to see from point Y a 4.7K to the plus side and a 2.2K resistor to the negative and ground side. And again, once we put this all together, that'll be a short. And if I can get all of this in the screen here pretty much, when we put these two circuits together, of course, this shorted node and this shorted node are the same. So I got X going here, and it's going through a 2.2K to the shorted load, and it's also going through a 4.7K to the shorted load, and we can call that ground. And point Y is going with a 4.7K to the shorted load and a 2.2K to the shorted load and ground. And so we have a circuit here that's going to wind up being something we can solve. Just happens to come out that way. And if we look at this circuit now, we have these two resistors in parallel and these two resistors in parallel. So the resistance from point X to point Y is going to be our Thevenin resistance. We learned before that that's also the same as our Norton resistance, and it's going to be R1 in parallel with R3. That combination is going to be in series with R2 in parallel with R4. Well, basically, these two parallel combinations are going to be the same because they both consist of a 2.2K resistor in parallel with a 4.7K resistor. And when you do 2.2 times 4.7 divided by 6.9, their sum, you'll wind up with 1.5K. We're going to have two of those, so it's going to be a 3K R Thevenin. So RXY equals R Thevenin equals R Norton equals 3K. Great. Now, if you remember in step 4, we put the load, or we put the source back in, leaving the load out still, and we compute the open circuit load voltage. Well, we actually can do that in this circuit because we can compute the voltage at point X, we could compute the voltage at point Y, both with respect to ground, and then subtract them and get the voltage difference from X to Y. So the open circuit load voltage is Vx minus Vy. All right, and we're going to use the voltage divider rule for Vx and Vy. So Vx, that's the voltage divider rule, but it's not really that tricky. I take Vs, which is our 2.5 volts, I divide it by V1 plus, divided by R1 plus R3, and so I got this voltage divided by this total resistance, and I have the current flowing down through that branch. When I multiply that current by R3, I wind up with the voltage from X to ground. And we carry that out and we wind up with 1.7 volts. I do the same thing with Vy. Vs divided by R2 plus R4 is the current going down this leg. I multiply that by R4 and I get the voltage from Y to ground. And so once again I do that, I get 0.8 volts, and VTH is equal to Vx minus Vy, and I get 0.9 volts. Okay, and so we now have our Thevenin circuit. It's got a series resistance of 3K and a voltage source of 0.9 volts. And when we put that in the circuit with the load resistor, we will have, here's our open load circuit. Here we are putting the load resistor in. Again, the voltage divider rule will give it to us. 0.9 volts, divided by the total resistance in this circuit gives us a current that's going to flow there. You multiply it by 4.7K and you get this voltage across our against 4.7K and RL, and we get 0.55 volts. And what I'm going to do now is I'm going to slide my A-down board in here. You can see that I've got the A-down 1000 in there, and I'm connected to, let's see if we can actually get it down here. Maybe it'll focus. It does some amazing things. Okay, yeah, there we go. It's got 2.5 volts on the orange and ground on the black. Alright, and then I'm going to bring this over here. And what we have here is we have a 2.2K resistor to the X place right there. This is node X right here, and a 4.7K to our ground, and we've got just the opposite over here. We've got a 4.7K from the power supply, 2.5 volts to Y, and a 2.2K to ground, and then I've got a 4.7K as the load. Now if I take out the load and I put a voltmeter in here, let's make some voltage measurements. I'm going to raise this up and hopefully we can still see what's going on here. That's awfully bright, isn't it? Maybe I can shade that a little bit. If I look at the open circuit voltage now, we want to see 0.9 volts. Well, first let's look at what voltage is across this thing. And 2.49, we're going to call that 2.5 volts. And now we're going to go from X to Y, and instead of 0.90 I got 0.91, pretty close. And now that was our Thevenin voltage, 0.9. Now I'm going to replace the load resistor here, and we're going to measure across the load resistor 0.556. We had 0.55, and I did a simulation. It comes out about 0.553 because we did a little bit of rounding off in there. But there's our solution to our circuit, and I suppose we could have hooked up channel A and B and done the voltage measurement, but I thought this was sufficient just to use a voltmeter. So there's a solution of our bridge circuit. This is very similar to the one in the homework. I can't remember what resistors I used in the homework. Maybe I even used the same ones. I don't know. But I wanted to solve it and show you that this kind of thing can be solved. As we go forward, we'll see with superposition and with some algebraic stuff, we can solve some fancier circuits, and then I think we'll leave the circuit equivalent theorems alone, having covered them, and move on to some other topics. So until next time, I wish you the best, and let's see. There you go. You can focus in on the resistors. All right. Catch you next time. Be safe, and we'll be in touch.